Very few things in life are constant. In physics, however, one constant is the energy content of the universe. After watching this video, you should be able to describe potential energy as stored energy between two interacting objects and apply the conservation of energy to a simple process. You will get the most out of this video with an understanding of kinetic energy. Understanding potential energy and energy conservation is important because energy is not only conserved on the vast universal scale, but also on much smaller scales, such as an acorn falling to the ground from a tree. Before we tackle the concept of energy conservation, we need to start with kinetic energy. Kinetic energy is associated with motion. Does the acorn attached to the tree have any kinetic energy? The correct answer is no. It does not have any kinetic energy when it is attached to the tree. When attached to the tree, the acorn is stationary and therefore has no kinetic energy. As the acorn falls, however, its speed increases as it gets closer to the ground. The acorn falls to the ground when it breaks its connection with the tree because of the attractive force of gravity between the earth and the acorn. This interaction force is present independent of whether the acorn is in motion and is what results in gravitational potential energy. There are other types of potential energy beyond that of gravitational potential energy, such as the elastic potential energy that is stored in a compressed and stretched spring due to the spring force, and electric potential energy, which is stored between electric charges due to the electric force. Near the surface of the Earth, gravitational potential energy, shown as the symbol U sub g, is defined as mgh. In this equation, m represents the mass of the object, g represents the acceleration due to gravity, and h represents the height of the object relative to a 0 point. Note that together, mg represents the force of gravity, reminding us that this potential energy is based on the gravitational interaction. This means that the acorns in this tree all have potential energy before they fall. The higher an object is, the more potential energy it has. Once they fall, however, the height decreases, and so does their potential energy. Where did this potential energy go? The correct answer is that the potential energy changes into kinetic energy. According to the principle of conservation of energy, the energy of a closed system, such as the acorn Earth system shown here, remains constant. For the examples discussed in this video, we are only considering two basic types of energy that are relevant to a falling object, that is, kinetic and gravitational potential energies. This means that while the acorn falls, the type of energy can change, but the total energy cannot change. As the acorn falls, the potential energy changes into kinetic energy. A bar diagram is sometimes useful to visualize the energy conversion. At the start of the fall, the energy of the system is all potential energy and no kinetic energy. Before hitting the ground at the end of the fall, the energy of the system is all kinetic energy with no potential energy. And in the middle of the fall, there are both types of energies. In every case, the potential energy plus the kinetic energy add up to the total energy of the system, which remains the same throughout the fall of the acorn. This type of energy conversion can go both ways. Take a ball thrown vertically, for example. At every point in the path, on the way up and the way down, the potential energy plus the kinetic energy of the Earth ball system adds to a total constant energy. Okay, let's recap the key aspects of potential energy and energy conservation. We set out to describe potential energy as stored energy between two interacting objects and apply the idea of conservation of energy to a simple process. Despite the ever-changing world around us, we can be certain of one thing. The laws of physics, including the law of conservation of energy, always apply.